So in this video, we're going to take a look at some special right triangles. Now the theme of this chapter is trigonometry, which is technically, measuring triangles, but it's always concerned with right triangles specifically. So in the first section, we looked at Pythagorean theorem. Today we're going to take a look at two very specific right triangles that happen to show up a lot in geometry and other subjects. The first one is going to be created by taking a square and drawing one of its diagonals. What ends up happening in this picture, because we have a 90-degree angle in the corner, and because we have two sides, the two sides of the square are congruent, we actually know that the two angles here would also be congruent. So therefore, these two angles, the two congruent angles, must be complementary. They must add up to 90 degrees. The only way to do that and be congruent is for both of them to be 45 degrees. So this is our first special right triangle. We call it a 45-45-90 triangle. All right, now let's find out what's special about this triangle. Let's try to use Pythagorean theorem to solve for the diagonal, for the length of the diagonal. All right, so the length of the diagonal would end up being the hypotenuse. The other two sides would be the legs. So we can do 5 squared plus 5 squared, and that would have to equal, we'll call this x, so that would have to equal the length of the diagonal squared. Well, 5 squared is 25, so 25 plus 25 makes 50. So therefore, the length of the diagonal would have to be the square root of 50. Now, we could leave it there, but I want you to simplify your roots in this chapter. So let's go ahead and try to think of a way we can simplify the square root of 50. Now, usually when you simplify a square root, you want to break 50 up into two numbers, like you want to break your number up into two numbers that multiply together, but you want one of those numbers to be easily square rootable so you can pull it out of the square root. Well, 50 has a nice square as a part of it, because 50 can be broken up as 25 times 2. Now, if you do that, you can break the square root up into both of the square roots separately, and then when you see the square root of 25, you know that that can just become 5 square root 2. So the hypotenuse, or the length of the diagonal in this case, is just 5 square root 2. That might not seem like a very interesting conclusion, so let's take a look at another example. It's still a square. We still have a 45-45-90 triangle, but now I've made the side lengths 8. So let's try calculating the length of the diagonal again. Well, once again, this is the hypotenuse. We'll go ahead and call that x. So we would do 8 squared plus 8 squared equals x squared. So that's 64 plus 64, so that would make 128. 128 equals x squared, which means that x equals the square root of 128. Now this one's a little bit tougher, but once again we want to try to simplify the square root of 128. So what can 128 be broken up into? Well, if you look back at what we did over here, 128 was literally just 64 plus 64. So that means that 128 could be represented as 64 times 2. And since 64 is an easily square rootable value, we can pull that 64 out and actually square root it. So when you pull the 64 out of the square root, it becomes an 8, and the 2 stays behind. So this is an interesting conclusion. The length of the diagonal is 8 square root of 2. The length of the legs was 8. We actually saw this exact same thing happen with the 5s. When the length of the leg was 5, the length of the hypotenuse was 5 root 2. When the length of the leg was 8, the length of the diagonal was also 8 with a square root of 2 attached to it. So what that means is that every 45-45-90 triangle has the same relationship. Not only are the legs of the 45-45-90 triangle congruent, but the hypotenuse is just square root of 2 times whatever the leg is. So that brings us to two relationships here. First, we have leg 1 equals leg 2. Now that's That's pretty obvious because it's an isosceles triangle. But the second one is the one we really want to focus on here, and that is that the hypotenuse will always be whatever the leg value is times square root of 2. And of course, if you want to use that the backwards way or the inverse way, you could divide that square root of 2 over to the other side, and so then you could say that the leg would be equal to the hypotenuse divided by square root of 2. Now let's try this out in a couple examples to see if this makes sense. Let's find the missing side lengths of this triangle. So we can see that it's a 45, 45, 90 triangle, and we were given a leg value. So right away we can solve out that the length of BT has to equal the same as the other legs. So BT has to be 13. Leg 1 and leg 2 have to be congruent. Now that we have that, we can solve for the hypotenuse. So the hypotenuse is equal to the square root of 2 times one of the legs. So since we know the leg is 13, we can find then that the hypotenuse would be equal to the square root of 2 times 13. In other words, we could just write this as 13 square root of 2, and that's it. You don't even have to type it into the calculator. You don't have to get a decimal answer. You can just go 13, 13, 13 square root 2. Now that's when you have the leg given to you. What happens if you have the hypotenuse given to you? Well, it's still got the same relationships. The hypotenuse is still going to be square root of 2 times the leg. But in this case, instead of being able to plug in a value on this side of the equation, we're just going to plug one in on the other side. So the hypotenuse is 10, and we're trying to solve for the leg. So in this case, we want to get the leg alone. We're going to have to divide by root 2 on this side and root 2 on this side. So that tells us that the leg would be equal to 10 divided by square root of 2. Well, that technically is the answer, and I would give you probably about 80% of the credit for that answer. But for a full credit answer, I'm going to ask you to simplify this expression. And you might remember this from Algebra 1 class. We want to get rid of that root that's in the denominator. It's called rationalizing the denominator. Because the square root of 2 is an irrational number, this fraction has an irrational denominator. But if we can, we want to get the denominator to be just an integer. So the quick way to do that with square roots is to just simply multiply by whatever square root is in your denominator on the top and bottom of a fraction. Watch what happens. The 10 multiplies by the square root of 2. 2 just be 10 square root 2. And on the bottom, the square root of 2 times the square root of 2 becomes the square root of 4. Now, at first glance, it doesn't look like we rationalized the denominator, but once you realize that the square root of 4 is just the number 2, you can see that there's no more roots in the denominator. And a lot of times when we do this, we can actually then simplify the top number and the bottom number. 10 can divide by 2, and so we can actually write this in a much simpler form. We can say it's just equal to 5 square root 2. So the leg here is 5 square root 2. And the leg here is also 5 square root 2. Did you notice that we're not using any Pythagorean theorems here? That's what makes special right triangles so nice. Once you know the ratio that's involved in the triangle, you don't have to go through some, multi-step process. All you have to do is either multiply by square root of 2 or divide by square root of 2. All right, now I told you we'd be looking at 2 special right triangles, so let's take a look at the second one. This time around, we're not going to start with a square. We're going to start with an equilateral triangle. And we are going to drop an altitude down straight from A to B so that it would have a perpendicular angle at the bottom. That's the definition of an altitude. All right, what kind of a triangle does that create? Well, we know that this angle is 90 degrees. Because this was an equilateral triangle at the beginning, we should know that this is 60 degrees. And that makes this angle up here 30. So this is the second special right triangle. It is called a 30, 60, 90 triangle. All right, let's see if we can investigate the measurements here. Let's go ahead and start with a side length out here of 8. Now, of course, that means that this side length would be 8, and it means that CB would be a side length of 8 as well. Now, when that altitude drops down in the middle of an equilateral triangle, it does something special to the side that it intersects. It actually hits it right at its midpoint. So our first connection here can be that the length, let's see, if we call this point in here point D, the length of DB has to be 4, and the length of CD has to be 4. So that side CD is getting split up into 2 congruent parts. But there's still another side to the triangle that we don't know. I'll go ahead and call that X. It's the altitude length. We can use Pythagorean theorem to solve this. So since 8 is the hypotenuse, we've got to put the X squared with the 4 squared, and we have to put the 8 on its own on the other side. So that gives us X squared plus 16 equals 64. We can subtract 16 on both sides, which gives us X squared equals 48. And then we can simplify, or sorry, not simplify, but finish solving by doing the square root. Now, just like before, the square root of 48 doesn't seem like a very interesting answer, but if we simplify it, we might be able to find out something neat. Well, you may not know this right off the top of your head, but 48 can actually be broken up into 16 times 3. Since 16 is an easy number to square root, let's pull that outside the square root. When you do the square root of 16 and pull it out, it becomes a 4. So we could represent the length of the altitude as 4 square root 3. Do you think it's a coincidence that this one came out to have a 4 in it and the side here was also 4? It's not a coincidence. In fact, a 30, 60, 90 triangle has some pretty similar connections between its sides. If you compare the hypotenuse side to this side down here, let's go ahead and call this the short leg because it's the shorter of the 2 legs. If you compare the hypotenuse to the short leg, you can see that it will always have a ratio of 1 to 2. The short leg is half of the hypotenuse, or the hypotenuse is double the short leg. When you compare the short leg to this side over here, which I guess we can call the long leg, you can see there's another simple comparison. 4 for the short leg just simply has to get multiplied by square root of 3 to create the long leg. Or vice versa. The long leg, 4 square root 3, would have to get divided by square root of 3 to create the short leg. So that brings us to our 30, 60, 90 ratios. Relationship number 1 compares the hypotenuse to the short leg. The hypotenuse is always 2 times the short leg, or the inverse way of saying it would be the short leg is 1/2 of the hypotenuse. And then the second relationship we see is that the long leg is always equal to the short leg times square root of 3, or the inverse way, the short leg is equal to the long leg divided by square root of 3. Let's take a look at a couple examples to see if this idea makes sense. Let's find the missing side lengths in this triangle. So let's fill in the 30-degree angle here, and let's identify our sides. Across from the 90-degree angle would be the 17, so that's the hypotenuse. We can tell that y would be the short leg, not just because it looks like it's the short leg, but also because it's across from the smallest angle. That means the one that's across from 60 has to be the long leg. All right, so we were given the length of the hypotenuse, and there's only one equation that uses the hypotenuse. The hypotenuse is equal to the short leg times 2. So let's plug 17 into the correct location in our equation, and let's solve. 17 equals short leg times 2. We need to solve for the short leg. In this case, it's y. So we need to divide by 2 on both sides. That gives us that the short leg has to be equal to 17 over 2. In other words, y equals 8.5. All right, now that we have the short leg, we can actually go ahead and use the second relationship for a 30, 60, 90, and that is that the long leg equals the short leg times the square root of 3. So plug in the value that you know. You know the short leg is 8.5. This calculation is really easy. The long leg equals 8.5 times the square root of 3. That's it. You don't have to calculate anything. Don't have to type it into your calculator. You can just say that the long leg is 8.5 square root 3 because it's whatever the short leg is times square root of 3. Some of these questions can go ridiculously fast if you know your ratios well. Now, the last one that we're going to look at is probably about as hard as I can make this in this video, okay? So take a look at your 30, 60, 90 triangle. First thing you should always do is identify your sides. So across from the 90-degree angle is the y. That's going to be your hypotenuse. Across from the smallest angle will be your short leg. And then across from the 60 will be your long leg. So in this 30, 60, 90, we were given the long leg. So we are forced to use the long leg relationship. So the long leg equals the short leg times the square root of 3. So let's plug in 12. 12 would go in here, and we need to solve for the short leg. The only way to get the short leg alone is to divide that square root of 3 over to the other side. So that tells us that the short leg will be equal to 12 divided by square root of 3. Now, technically, that is a final answer, but remember, that's only an 80% answer. I'm going to give you full credit if you can rationalize that denominator. So just like we did in an early example, we are just going to simply multiply by whatever square root is in the bottom on top and bottom of another fraction. So 12 times square root of 3 across the top is just 12 square root of 3. And then on the bottom, square root of 3 times square root of 3 would be square root of 9. Once again, that bottom square root simplifies to be an integer. And now we can we can simplify 12 with 3. 12 divided by 3 means that this is just simply 4 square root 3. So the x value here, or the short leg, is 4 square root 3. That one took a little bit of work, but the next calculation is going to be really fast because the other relationship for a 30, 60, 90 is that the hypotenuse equals the short leg times 2. So we can plug in the short leg, 4 square root of 3 times 2, and that's going to equal the hypotenuse. 4 square root of 3 times 2, you just multiply the numbers that are outside the root. So the 4 times 2 makes 8, and the other part is just, it doesn't change, it just stays square root of 3. So y equals 8 square root of 3. All right, in the next video, all I'm going to do is go through a few more examples of this in case you feel like you'd like to see some more, in case you have more questions and you'd like to see a few more workings of 45, 45, 90 and 30, 60, 90.